Panama Engineering for Capstone Senior Design. Our project was to design a stormwater system for the Pacific Beacon military housing. During this presentation, we will highlight several aspects of the project. My name is Jesus Ortiz, and I worked on hydrology.
My name is Jose Limon, and I worked on hydraulics.
My name is Jose Sanchez, and I worked on land development.
And my name is Ricardo Rodriguez, and I also worked on land development.
The primary task of Panama Engineering was to design a stormwater system for the Pacific Beacon Bachelor Enlisted Quarters, which would comply with the County of San Diego standards.
The Pacific Beacon BEQ is approximately a 16-acre site located on the Navy base of San Diego, California. Pre-development conditions are open space and a golf course within the Navy base. Post-development conditions will be exclusive housing for single enlisted military personnel. This site will include 3 18-story buildings, 1 parking structure, a parking lot covering 3.1 acres of the site, and an athletic field.
One major issue due to post-development will be the increase in surface runoff. Due to the new conditions, it was determined that the surface runoff will be routed by a gravity flow system. However, this was a major issue because of the flat terrain. For this problem, our group came up with 2 possible solutions.
For calculating the hydrology aspect of this project, we used the rational method as specified in Section 3 of the San Diego County Hydrology Manual. Using the equation Q equals CIA, where Q is the discharge, C is the runoff coefficient, I is the rainfall intensity, and A is the drainage area, we calculated discharges for existing and proposed conditions. We calculated the discharges using a 25-year storm event for the project area and a 100-year storm event for the detention basin. For existing conditions, the area was broken down into 13 subregions, and the total discharge was about 15 CFS, while the proposed area was broken down into 15 subregions, and the total discharge was about 44 CFS. Since the discharge for the proposed conditions will be more than for the existing conditions, detention was necessary. Following Section 6 of the San Diego County Hydrology Manual, a hydrograph was produced to determine the storage volume of the detention basin.
Our first alternative was designing an underground detention basin on the northern corner of the site, which would have served the purpose of filtering the water as it exited the site and into the existing offsite facility.
The second alternative was the combination of a detention basin and the placement of 3 rain gardens throughout the site. This solution would allow for the routing of surface water into the rain gardens to be filtered. After entering the rain gardens, a certain amount of the volume would percolate through the soil and help replenish groundwater. The excess volume would then be routed with gravity pipes to the detention basin. After some consideration, we decided to go with the second solution because it would cost significantly less and water quality would improve.
Designing the stormwater system was a major issue since the water quality would need to be improved before exiting the site. First, we would need to route the surface runoff to the rain gardens and then to the detention basin before allowing it to enter the existing off-site system. This caused a major issue since the system will be based on gravity flow and the post-development terrain would be flat.
With the stormwater system, we had the option of dividing the site into two areas and allowing the southern section to enter the existing system immediately without treatment, or lowering the detention basin by 7 feet to allow proper function of the gravity pipes. After going with the second option, we decided to have the detention basin serve two functions, which included using it for detention and as a sports field. The detention basin would therefore concentrate the volume in one location and release it at the same rate as pre-development conditions. The hydraulics portion of this project involved the design of several catch basins and pipes. To design the pipes, we used Manning's equation to determine the size of the pipes for different areas of the project. By rearranging the equation, we can solve for the diameter of any pipe we want as long as we have the other information needed in the equation. With S being the slope of the pipe, A the cross-sectional area of the pipe, R the hydraulic radius, Q the discharge, and N the roughness coefficient, which in this case was 0.013. For this project, the two types of materials chosen for the pipes were reinforced concrete and polyvinyl chloride, which is also known as PVC.
The detention basin was designed using the 100-year 6-hour storm event and with a stretch length to width ratio. The dimensions for the basin will be 319 feet in length by 158 feet in width by 7 feet in height, resulting in a length to width ratio of 2:1 with a capacity of 350,000 cubic feet. The length to width ratio helps provide time for pollutants to settle before reaching the downstream outlet pipes. As the rate of runoff begins to exceed the detention capacity of the combined treatment system, flow will exit the northwest corner of the detention basin into the mainline system. The discharge water entering the basin will be 36 cubic feet per second, and the exiting discharge will be 8 cubic feet per second.
A rain garden is a man-made or natural depression which detains and filters stormwater runoff from impervious surfaces, such as rooftops and driveways. It is considered to be a best management practice that is designed to be aesthetically appealing and naturally incorporated into the landscape. A rain garden may also be referred to as a bioinfiltration or bioretention cell.
The benefits of using rain gardens are the following: reducing stormwater runoff as well as treating it on site instead of allowing it to immediately enter the storm drain system, increasing water infiltration, which results in more water entering the soil and less pollution entering the streams, water and energy conservation, and wildlife habitats being created and aquatic ecosystems being improved.
In order for Panama Engineering to accomplish its primary task of designing a stormwater system for the project, first we had to provide an adequately graded site to route all the surface runoff into collection areas, such as vegetated swells or catch basins. Due to the flatness of the site and our need to comply with the San Diego County standards, our design required us to maintain a 1% slope in parking lots and roadways. One option for the parking lot and driveways was to use pervious asphalt or pervious concrete, but both were discarded due to the cost and the presence of soil type D on site. Since asphalt material is difficult to construct to a further precision, it was determined that a 1% slope was suitable to avoid water puddles. Said solution also had the benefit of reducing the volume of cut or fill that would be required at the completion of the project, and therefore reducing the cost.
This